conference in uh, while I was in the a RAD conference. Um, it turned out to be that I was approached by the IAEA to come out with an outreach as well. Anyways, I'm going to be talking about the history of nuclear science and impact of Nobel Prize winners. The terminal training objectives are the description of history of nuclear science. Of course, the enabling training objectives are the detailed internet literature search, which I've come up with over the past years. I'll tell you who I am not. I am not the greatest tennis player in the world. I'm not Milan Lucic, who used to play hockey. I'm certainly not Nikola Jokic. I'm definitely not Nikola Tesla, and I'm definitely not Petrovic. There's a picture of myself here on the right-hand side, having a Tesla t-shirt. Well, everyone really knows, has a good feeling about the origins of the elements, and there's been a lot of information that's come out in the last about 6 or 7 decades of coming out of how the elements came around from the cosmology aspects. Here is a table which you can see of the origin of the elements, looking at the different types of ways that they came about. They're the primordial ones, the Big Bang Theory, et cetera, et cetera. And it's don't want to spend on time on each particular type of element. We're all very familiar with the P process and the R process, and I really won't get into that too much, but just to basically tell you that things started off with protons and helium, and then from that, everything went on. And you can see these very nice diagrams on the top as well as in the middle. Further work done on the R process and S process gives a little bit of a better understanding of the cosmology and the elemental abundances, or the relative abundances of the chemical elements in the solar system. So essentially, the understanding of the cosmology and the birth of elements has to do with nuclear reactions. It didn't happen one day. One scientist woke up and said, "Hey, I think I have a way of being able to come up with the chemical elements." It was all based on nuclear physics, fundamental nuclear physics, and nuclear reactions. So this particular lecture is to give you a historical concept. It's very non-technical from here on in. Around 440 BC, Lysippus of Miletus originated the concept of atoms. He and his people, Democritus, where obviously comes the word democracy, of Abdera, refined and extended this idea for many years. And Democritus lived from 460 to minus 371 BC. Epicurus, from 341 to 271 BC, taught that the theory that the basic constituents of the world were atoms, uncuttable bits of flying matter that traveled through empty space. He himself tried to explain this phenomena in atomic terms. Now, let us understand, this is more than 2 centuries ago. I mean, over 2,000 years ago, and it had been a long time from what the Greek philosophers thought all the way up to the Renaissance, first in the Middle Ages, and then on to the Renaissance. So it was really some very advanced thinking by the Greeks. In Greek, the prefix a means not, and the word tomos means cut. Therefore, the word atom, therefore, comes from atomos, the Greek word meaning uncuttable. You can get a lot more information on the internet from the URL, which is shown below. Uh, the concept of atomism came about this way. Everything is composed of atoms, bits of matter that cannot be seen or further split into smaller portions. There is a void or empty space between the atoms. However, atoms are completely solid, and as we all very well know, atoms are homogeneous with no internal structure, and they are of difference in their size, shape, and weight. If you look a little bit more closely into the philosophy out in India, you have Jainism. There's a person called Paramantu who talked about infinitesimal points of space. Skanda in groups of Paramanas thoughts. Buddhism had two schools, Vaibhasika and also Sautrantika. Hinduism also had two schools, Nyaya and Vaisesika, as well. And they all began to think about things that couldn't be smelled or touched or handled either. And it was the beginning of this type of atomism philosophy. Very quickly, atomism in the Middle Ages. Isidore, who was the Bishop of Seville, Venerable Bede, Urbanus Maurus, William of Conches, and Vincent of Beauvau, they all showed the knowledge of atomic thinking in their writings. And again, this was the birth of science going ahead and being able to expand into trying to understand things and putting in a philosophical edge on things which could not be seen or touched or felt or smelt. So it was really the beginnings of those times. Atomism in the Renaissance, Nicholas of Cusa, Girolamo Fracastoro, Peter Ramus, Daniel Sennert, Pierre Gassendi, and Robert Boyle from Boyle's Law, P1 V1 is equal P2 V2. And in 1588, Giordani Bruno wrote about the indivisible natural things. So you can see that the Greeks had started it. There was really nothing more really talked about it, a little bit about the Indian philosophy, but it's only in the Middle Ages and then onwards to the Renaissance that people really started to put things together in the terms of atomism. Okay, so then we go out to our very, very famous scientist called Dalton, John Dalton out from England. And he said that all matter is made of atoms. Atoms are indivisible and indestructible. All atoms are of a given element are identical in mass and properties. He also said that compounds are formed by the combination of two or more different kinds of atoms, and a chemical reaction is a rearrangement of atoms. My own personal unsubstantiated view is that I happen to think that Dalton may have gone back to the Greek writings, and some of the comments that he wrote down are very similar to the comments that the Greeks had. I'm not saying that he stole their ideas, but I think that he may have, and I have no way of proving this, have looked at some of the previous Greek writings. The periodic table then came about in 1879. Dmitry Ivanovich Mendeleev arranged the order of their increasing atomic weights to show a periodic repetition of the properties. And so this was the very first attempt to put order to the elements. And at that particular time as well, not all the elements had been discovered. We then go on to this very famous fellow. He wrote a treatise on electricity and magnetism and came up with a very famous Maxwell equations. This is the very first book or paper which he wrote on that. He also came on later Heinrich Hertz, And he basically said, it gives me satisfaction to gain knowledge for myself and from others directly from nature rather than to merely learning from others and myself as well. And he then wrote his very famous paper on electricity, and his name, of course, was Hertz. Well, things really moved very fast afterwards. Classical mechanics and classical physics really began to tumble apart with the beginning of the X-rays. This was discovered by German physicist Röntgen in 1895. X-rays were seen from the glass walls of a cathode tube. This was made fluorescent by the impact of the cathode rays, immediately used from bone setting, and it was originally termed was the Röntgen machine and not necessarily the X-ray machine. My own mother, who came from Poland, always considered the X-ray machine to be Röntgen machine, where she grew up out in Warsaw. And of course, we see the very famous picture that he took of his wife's hand. He didn't use his own hand; he used his wife's hand, and you can see the marriage ring which she has on her fourth finger. 1 year later, radioactivity was discovered by French physicist Henri Becquerel in 1896. He left uranium salts next to a photographic plate, which then fogged and attributed this to the uranium atom. Of course, the very famous Becquerel was named in his honor, and as we all know, this is 1 disintegration per second. Polonium and radium, they were discovered by Pierre and Marie Curie in 1898. 1 metric ton, which is 2,000 pounds, of pitch blende was used to get a small quantity of radium. The term Curie obviously is in their honor, and it is defined as 3.7 times 10 to the 10th disintegrations per second in 1 gram of radium. A term which has historically stayed with us. Röntgen then, who was born in 1845 and died in 1923, he gets the Nobel Prize in Physics in 1901 for the discovery of X-rays. When it came to gamma rays, this was discovered by French physicist Paul Villard in 1900 while studying uranium. He deduced that these radium rays had greater penetration depth than the X-rays. Rutherford in 1914, who was born in New Zealand but did his discoveries out in England, called these rays gamma rays, which had a form of electromagnetic radiation. And we're all very familiar with the types of pictures below showing the inverse of frequency and wavelength. I should say frequency and energy. Henri Becquerel, who died in 1908, he gets the Nobel Prize in Physics, half a prize, for the discovery of spontaneous radioactivity. I want to go ahead and say how quickly people got Nobel Prizes. These days, you don't get a Nobel Prize in 3 or 4 years. You typically have to wait maybe 30, 40, or 50 years, to say the very least. One of our faculty members, who recently died at the age of 100, was the oldest living person to get the Nobel Prize. He got it for lithium-ion batteries, and it took decades for him to get it. Pierre Curie, Marie Curie, with her maiden name being Sklodowska, they get the Nobel Prize in Physics in 1903, a quarter of the prize each for the radiation studies discovered by Becquerel. J.J. Thomson, who died in 1940, he gets the Nobel Prize in Physics in 1906 for the discovery of the electron and conduction of electricity in gases. Rutherford then gets the Nobel Prize in 1908 for the study of decay of disintegrations of radioactive elements. So you see that things are really beginning to move around quite a lot. Marie Curie, who died in 1934, she gets the Nobel Prize in chemistry for the discovery of radium and polonium. And she really had a momentous life by being able to be the only woman among dozens of men who were in the field of nuclear science at that particular time. Well, artificial transmutation started off. Rutherford in 1917 detected the transmutation of one element material, nitrogen, into another, oxygen, which was induced artificially when the nitrogen atom was bombarded by the natural alpha particles of radium. And one of the greatest things about radium-226, which has a half-life of 1,630 years, is that it gave off alpha particles. And this was a source which was used extensively by all the early scientists to be able to produce various types of nuclear reactions. Charles Glover Barkla in the United Kingdom, he gets the Nobel Prize in 1917 for the study of the characteristic Röntgen or X-ray radiation of the elements. Of course, we have the very famous Max Carl Ernst Ludwig Planck. He comes up with the Planck constant. He gets the Nobel Prize in 1918 for the discovery of the energy quantum, which we're all very familiar with. Albert Einstein, Germany and in Switzerland, he's born, he died in 1955, I think in Princeton University in the USA. He gets the Nobel Prize in Physics in 1921 for the photoelectric effect. He did not get it for E is equal to mc squared, which we're all very familiar with. He gets his work in theoretical physics. Bohr, and later his son, who was also a very accomplished nuclear physicist, he gets the Nobel Prize in 1922 for the study of the structure of atoms and of the emanating radiation which comes from that. And we're all very familiar with the early works of the Bohr atom. The next major invention or discovery, I should say, came from Frederick Soddy in the United Kingdom. He gets the Nobel Prize in chemistry in 1921 for the study of the chemistry of radioactive substances and the origin and nature of isotopes. And on the right-hand side, you can go ahead and see his original diagrams showing the different alpha decays and beta decays. This was a way of taking the Mendeleev table and now beginning to make it more sophisticated with isotopes. Johannes Hans Wilhelm Geiger, born in 1882 and died in 1941. Him and Walter Mueller, they discover or they develop the Geiger counter, which is the standard counter, which is used worldwide by the hundreds of labs all over the world, and he has the GM counter. My closest association with Johannes Geiger is that his son was the division director at the National Research Council, where I did a postdoctoral fellow back in 1982 to 1983. And my boss's boss, who was a Geiger's son. So that's the closest I ever came to knowing someone famous. Well, there was another fellow who came around and he did a lot of work in trace applications in biology. And his name obviously was Hevesy, okay? He's often called to be the father of nuclear medicine. He has a very true story. in 1923, he demonstrated the distribution of radioactive lead in growing bean plants. And 1911, Hevesy suspected his landlady was recycling leftover food and serving them in new meals. To prove his theory, he secretly added a small amount of radioactive material in his leftover meat. A few days later, he used an electroscope to measure the radioactivity of a meal she served, confirming his suspicion. This experiment is significant because it's one of the first successes in radioactive forensics, what I call it. He's the real, the real first person who I think did nuclear forensics. Sagaman in Sweden, he gets the Nobel Prize in 1924 for his discoveries in the field of X-ray spectroscopy. Urey gets the Nobel Prize in Chemistry in 1934 for the discovery of heavy hydrogen, which obviously was quite important. Frederic Joliot and Irene Joliot-Curie, who was the daughter of Pierre and Marie Curie, they get the Nobel Prize in Chemistry in 1935 for the synthesis of new radioactive elements. Along comes Chadwick, and he finally figures things out. He discovers the neutron. Of course, there was a lot of problems in discovering the neutron because it had no charge, but if you could have a neutron interact with the target, then you can go ahead and put on a detector to look at the charged particles. Either protons or alphas were the two more common ones. So this was done in 1932. Victor Franz Hess and Carl David Anderson, they get the Nobel Prize in Physics in 1936, half a prize each. Hess gets it for the discovery of cosmic radiation, and about 8, 9, 10% of the natural occurring radiation which you get in your body comes from the skies. And the very important discovery of the positron by Anderson, and of course positrons are one of the mainstays in nuclear medicine. Artificial isotopes. Ernest Lawrence at the University of California, Berkeley invents the cyclotron. Irene and Frederic Joliot-Curie produced the first artificial isotopes. In 1935, Ernest Lawrence produces radioactive sodium isotope by using his cyclotron. Joseph Hamilton uses iodine-131 for diagnostic purposes in the patients, one of the very first discoveries. And in 1942, during World War II, the nuclear reactor is constructed and operated at Oak Ridge National Laboratory, and that was part of the very large Manhattan Project. Fermi, he gets the Nobel Prize in 1938 for the discovery of nuclear reactions by slow neutrons and radioactive elements. At that particular time, there were lots of neutrons which were available, and as such, the physicists had a great time going into the lab and bombarding all various types of targets, and just to basically have a real curiosity of what all this meant. Lawrence gets a Nobel Prize in Physics in 1939 for the invention and the development of the cyclotron. Hevesy, he gets the Nobel Prize in 1943 for the use of isotopes as tracers in the study of the chemical processes, and that's one of the reasons why he was considered to be the father of nuclear medicine, but I also think he was the father of nuclear forensics. The making of the bomb in post-World War II. Otto Hahn in Germany, right in the middle of the war, he gets the Nobel Prize in Chemistry in 1944 for the discovery of the fission and heavy nuclei. We go onwards. Rutherford then He comes up with the model of the atom, which we knew from beforehand. Chadwick as well. He was from 1891 to 1974. They talked a bit about the various nuclear chain reactions, and lo and behold, they found that uranium is particularly good to absorb neutrons and split, for example, into barium and krypton isotopes. We're all very familiar with these types of sustainable um, reactions. Fission was discovered on December 17th, 1938 by Lise Meitner and Otto Frisch. They burst the atom and detected barium. Hahn and Meitner paper discovers the experiment about finding barium. And let me see if I can just move this up a little bit. Yes. And Meitner and Frisch paper describes the physics. Actually, she was his aunt, rather strangely. Let me see if I can go down here. Hmm. Uh, Having trouble going down to the next slide. There we are. Oppenheimer, he died in 1967. He was a professor of Berkeley. He created the Atomic Energy Commission in the United States. He lost his security clearance. President Kennedy, at that particular time when he was in office from 1961 to 1963, reconciled with him and gave him an award. And of course, we all know of the many different types of scientific accomplishments that he had. It's important to talk about the making of the bomb and also some of the post-war uh, nuclear physics, which I call sometimes the Cold War, the Manhattan projects. Berkeley had calutrons to separate uranium-235 from uranium-238. Los Alamos was asked to have a bomb design and also a bomb production. The Hanford was the water-cooled reactor to produce plutonium-239. It was built and operated by DuPont. Chicago was the first sustaining reactor built at the University of Chicago, and this was managed by Enrico Fermi. Oak Ridge had the uranium enrichment and diffusion, and Y12 at that time had the uranium enrichment, and Colotron at that time it was run by Easton Chemical Company. This is this very famous Easton company that came up with the Kodak cameras. In Hanford, they basically bombarded uranium-238 and eventually got plutonium-239. Of course, they had to run this 24 hours a day to get enough plutonium so that there be a sufficient critical mass. The first Los Alamos devices one was called the Fat Man, the other one was the Thin Man, and there was both on August 6th and August 9th, the Hiroshima and Nagasaki atomic bombs. You can get this easily off the internet. The uranium-235 Thin Man and Little Boy designs were out there as well. The Trinity test site came on July 16th, 1945. In a very famous statement, Oppenheimer says, "Now I am become death, the destroyer of worlds." The cost, the United States spent roughly $300 billion on World War II, and about 10% of that was spent on the atomic bomb at that time. Nuclear fission, of course, came about. Otto Hahn and Fritz Strassmann from Germany In 38, bombarded uranium with slow neutrons. In 1939, Lise Meitner and Otto Frisch, German refugees in Denmark, published the theory for nuclear fission. The U.S. atomic testing, as I said before, came on July 16th, 1941, and the Nevada test site at that particular time hosted the first atmospheric testing in 1951 and the last underground testing in 1992. The Marshall Islands, that included the first post-war series and later tests like Operation Greenhouse. The United States conducted over 1,000 nuclear tests from 1945 to 1992. The Russian atomic testing, the first test was called First Lightning and was conducted on August 29th, 1940. Let me see if I can move this about a bit. In 1949, at the Semipalatinsk test in Kazakhstan, and it was followed by the detonation of the Soviet hydrogen bomb on October 30th, 1961, and it's the largest man-made explosion in history. Russia, including the former Soviet Union, conducted 750 nuclear tests from 41 to 1990. Of course, we can talk about the tests that France did, the UK and China as well, and they were the original five countries that can do the nuclear testing. France's first atomic bomb was conducted in 1960 in Algeria. They finally tested over 210 atomic bombs, both in the Algerian Sahara as well as in the French Polynesia in the South Pacific. The UK did its testing in Montebello Islands in Australia. They tested less amount, about 45. And in China, they had their first testing in 1964. And China conducted 45 nuclear weapons tests from 52 to 91. Cold War nuclear physics continued. There was specific bomb testing at the Bikini Islands and Eniwetok Islands. In 1954, the Marshall Islanders received burns that caused leukemia and thyroid cancer. There was a ship, the Lucky Dragon Japanese fishing boat, received fallout. There were the studies of the psychology effects of battle use of tactical nuclear weapons were conducted. There were many famous scenes like this where soldiers descended into the blast areas and were permitted to move closer to ground zero. Air Force personnel flew planes through mushroom clouds. And in the early 1950s were the beginnings of the public resistance, including banning the bomb movements. In 1953, out in Yucca Flats in Nevada, the winds went the wrong way and sheep died in a neighboring state. In the 1940s, 50s, and 60s, many atmospheric tests were conducted, as I talked about. Finally, they came in 1963, the Atmospheric Test Ban Treaty. The Nevada test sites were chosen because they were remote, scarcely populated, and consistent weather conditions. One tragic event happened. There's a very famous movie, maybe not so famous, but certainly with a very famous actor called John Wayne. Almost 1/3 of the cast and crew members in the 1956 film A Conqueror had died because they were very close to an atomic testing facility. Well, enough of World War II and post-World War II. We go on to John Douglas Crawford and Walton. They received the Nobel Prize in Physics in 1951, half a prize each for the atomic for the transmutation of atomic nuclei by artificially accelerated atomic particles. Macmillan and Seaborg, they get the Nobel Prize in Chemistry in 1951, half a prize each for the discoveries of chemistry of radioactive isotopes. Nuclear medicine then comes around in 1951. Benedict Casson at the University of California invents the scintillascanner for the measurement of radioiodine in the body. This was the first step towards positron emission photography, called PET. Hal Anger develops his Anger camera, which is a strange name, but it was after his last name, which permitted visualization of radio tracer distribution in biological systems. Eisenhower comes up in 1953 for Atoms of Peace. He talks at the United Nations, very, very famous speech out there. And that was the beginning of the use of atomic understanding to be used for peaceful purposes. And the nuclear navy started. Admiral Hyman G. Rickover, who was born in Poland. His name was Chaim Godele Rickover. He received the Congressional Medal in 1959 in recognition of his achievements in successfully directing the development and construction of the world's first nuclear power ships and first large-scale nuclear power reactor devoted exclusively to the production of electricity. And for decades later, the design of the reactors for the nuclear navy were actually very similar designs that were used in the over 400 nuclear power plants. And the first nuclear submarine was called the USS Nautilus. Cormack and Hounsfield, they get the Nobel Prize in Physiology or Medicine in 1979. They get a half a prize each. And lastly, Josef Rotblat in Poland, who died in 2005, he gets the Nobel Prize in 1995 for the development of nuclear medicine. And you can go ahead and look at all the Nobel Prizes in the nuclear sciences which were out there. Anyways, I know that I kind of talked a lot about the history. I always think a lecture like this, which can have many different avenues, should really be introduced in everyone's different types of courses. It doesn't have to be a nuclear course. It can be a course on mechanics or a course on electrodynamics, or the case. So this is just an idea that I always used very successfully the first, second lectures to be able to get these students interested in the subject matter. Thank you very much. I know I went a few minutes over, but sorry for that.
Thank you. Thank you for that. Thank you, Professor Landsberger, for this wonderful presentation regarding history of nuclear science and related Nobel Prize winners in this field. So any questions? At the moment, maybe I can ask you about your opinion about future of this field, of the fundamental as well applied nuclear physics, for example, in comparison with high energy physics experiment in the future.
Well, you know, I always think of two main areas. I think fundamental understanding of physics, high energy physics, low energy physics, is really very critical. Because if you want to go and have some real advancements in all types of applications and in technology, I think having a very good, strong basis in physics. I always make this joke of how you can make a physicist into an engineer, but you can't necessarily make an engineer into a physicist. So I think that's really very good. Applications in nuclear medicine will only increase, and of course, with small modular reactors coming about as well.
Okay, thank you. Okay.
Yeah, I see that we have our next speaker coming up, so I will say goodbye and hope to see you sometime in spring next year, Dusan.
Yes, see you in spring next year. Thank you very much once again.
Thank you. Bye-bye.